Hi, and welcome to 3.3 Free Fall Up, Then Down. Students will be able to calculate and fully describe the motion of an object being thrown upward and then being caught. Being caught from the same location from which it was thrown, to be precise. So, for example, critical thinking, a ball is thrown straight upward, then is caught at the same height from which it was thrown. The ball is in the air for a total of 2 seconds. Looks like that. That's if LeBron James in his younger days when he was playing for the White Plains Tigers. All right. The question is, how many seconds does it take to reach its maximum height? Now remember, you are neglecting friction. You don't care about air resistance. So if it's completely symmetrical, it comes to the same height from which it was thrown, and it takes 2 seconds. What do you think? It takes 1 second to go up to the maximum height, and then 1 second to come down. Okay, so that's the first part of the symmetricality of the up then down to the same height, is that it's half the time up, half the time down. Now compare the ball's initial and final velocity. So what is the initial velocity? First of all, is it positive or negative? The initial velocity is pointing upwards, and it actually comes back down with the same magnitude, but it's moving in the opposite direction now. So because everything's symmetrical, it's caught from the same height from which it was thrown. It has time to accelerate downward and pick up speed, and it gets to the same speed, but it's moving in a different direction. So here's the same situation again, except it's five. Now we're telling you the initial velocity is 5 meters per second. The ball's thrown up and reaches its maximum height where the velocity is 0, like we talked about yesterday. So yesterday we said, okay, VF is 0. VI is positive 5. VF is 0. A is negative 9.8. Then the ball drops down to where it started. This can be viewed as a separate problem. And why would that be useful to you as a physics student? Why would you want to look at the second half instead of the first half? Well, if you look from the top down, the initial velocity is now known. You know the velocity at the top. So let's look at our analysis from the top down. The do now told us how important VI is because it's in all of the equations. So if you know VI, that's better than knowing VF for the equations that they give you in the reference table. And don't forget, if the problem says, oh, it's thrown upward with a velocity of 5 meters per second, then you also know the final velocity when it comes back down is just going to be negative 5 meters per second in the opposite direction. So simply put, the time up is equal to the time down. We talked about that on the previous slide. It's symmetrical. And VI up is equal to negative VF down, like we just said. And don't forget, the velocity at the top is 0, which you, as a savvy physics student, can either make it VI or VF. Or if you really wanted to, you can say, okay, the initial velocity is 5 meters per second up, and let me make the final velocity. I want to look at the whole path, negative 5 meters per second down. Sure, it reaches a velocity of 0 during its trajectory as it goes up and down, but let's say you wanted to find the total time, the whole trip, then I would probably make VI positive 5 and VF negative 5, so it gives me the whole thing instead of saying, okay, let me look at the top going down. That's half of the trip. And then let me find that time. That's only half the time. Then you'd have to multiply by 2 to get the whole picture. It depends on what the question's asking for. It depends on what the question gives you. But I'm giving you an overview of what's really happening and what is known and what is unknown in a typical situation. All right, so let's see what this looks like in action. It says a ball is thrown straight upward. It takes 3 seconds to come back down to its starting point. What is the ball's maximum height, the final vertical velocity, the initial vertical velocity, and then we'll draw some graphs for this motion. So in physics, it helps to really draw a picture when doing this. So the ball goes up, and then it comes straight back down, but that's kind of confusing. So even though it's a linear motion, I kind of like to draw it off to the side so we know that, okay, then it comes back down over here. We know at this point the velocity is 0 meters per second. We know the acceleration is negative 9.8 meters per second squared. They told us that the time for this entire motion is 3 seconds. So I'm going to call that the total time because we might end up doing that savvy physics move and dividing the time in half, which would look like this. I draw it like this. Okay, if we're looking at the first half, then VF becomes 0, and we know that. We could also decide to look at the second half, where the initial velocity, we're starting our analysis at the top, where the initial velocity is 0, and then it accelerates and gets faster to a final velocity over here. And we know the acceleration, and we would know the time. So it depends on what the question's asking. If you want to look at the first half or the second half, or even you could look at the whole motion because we know that is 3 seconds. So this is the whole thing here. So we're looking for the maximum height though. So anytime they're looking for the maximum height, it's just like yesterday's problems where, okay, we know the velocity is 0 here. Let's make sure we make that one of the parameters because at this position, that's where the maximum height is. So we want to make sure that we're using the velocity is equal to 0 meters per second. But again, do we want to look at the first half and make that the final velocity? I don't think so. I think it'd be more helpful to look at the second half of this motion and make that the initial velocity. Just like we saw in the do now, it's more helpful to know the initial velocity because it's in all of the equations. So the initial velocity is better to have. And again, we're looking for the displacement, and we'll look for the equation that doesn't have VF in it, which is D is equal to VIT plus 1/2 AT squared. You plug in your numbers. So the initial velocity is 0. That term's going to go away. But what time should we plug in? Am I going to put a 3 over here? There's something else we didn't really talk about. You know, the total time is 3 seconds. But if we're only looking at the second half, we need to look at the second half of the time. And we said in the beginning that it's symmetrical, so you just take that total time and divide it by 2. So we're making VI equal to 0. So we're going to plug in 1.5 here and 1.5 right here. And you get a displacement of negative 11.025 meters. The math pops out a negative number. But the question says, what is the maximum height? And I've never said, oh, the height of that thing is negative 11 meters. See, the math is just doing what the math does, and you're telling it that it's starting here and accelerating downward. So that means that you're starting here and you're accelerating downward in the negative direction. So if you wrote that on your answer, that's totally fine. I know what you mean, but you could also say, okay, the maximum height is 11 meters. I'm answering the question. I'm rounding it, so we'll round that answer. Equals 11. Then the question asks, what is the ball's final vertical velocity? So that's at this position here. What is the final velocity? So now we're looking for that, and we have a couple different options. Let's start here again. We're ending here. We're going to use half the time because we're only looking at the second half of the motion. So in this case, since I rounded the displacement, I'm going to find the equation that doesn't have the D in it, and we're going to do VF is equal to VI plus A times T. Again, we're looking for the final velocity. The initial velocity is 0 because we're looking at the second half of the motion, negative 9.8. And again, this is half the time that is given in the problem because we're looking at only the second half. So you do the calculation and you get negative 14.7 meters per second. So that's how fast it's going. at this position here. Regardless of if you're looking at the first half or the second half, at that position there, it's definitely negative 14.7 meters per second. So now it says, what's the ball's initial vertical velocity? And guess what? We already know the answer. VI is equal to, do you know what it is? Well, it's just going to be positive 14.7 because it's symmetrical. You're catching it at the same exact height. So it's the same magnitude but the opposite direction. But can we prove that? Yes, we can. So I'll actually, you know what would be fun is if we don't do the halfway and we look at the whole picture now. So yeah, we know the velocity at the top is 0, but just because we know that doesn't mean we have to use that piece of information. We can say, okay, the time they tell us is 3 seconds to go from here to here. And we're going to pretend like we didn't predict what the answer was. Let's see if our prediction is correct. So that's supposed to be a question mark over there. It looks like a 3 with a dot underneath it. What is the initial velocity? Let me clean this up a little bit. So the acceleration is still negative 9.8 meters per second squared the whole time. We're looking at the whole path, so we'll use 3 seconds. The final velocity we'll use negative 14.7 meters per second, and let's look for that initial velocity. So we could actually use the same formula, VF equals VI plus AT, but now we're plugging in different parameters because we're looking at the whole path. The final velocity we calculated before was negative 14.7. The initial velocity is what we're looking for. This is negative 9.8, and we're looking at the whole path, so this is 3 seconds. So you end up getting negative 14.7 is equal to VI minus 29.4. And when you add 29.4 to both sides, you end up getting an initial velocity of 14.7 meters per second, positive, just like we predicted. All right, so that's cool. And if you look at the way these formulas set up, it actually kind of makes sense, right? Because this is half the time, this is the full time, and it's actually nice how the math works out if you sit there and look at it. There is another piece, if we're going back over here, and I'm going to do the graphs too, but if we come back over here, there's another piece of information that we know without having to do any calculations. If we're looking at the whole path, we started here, and then we ended up at the same position that we started. And remember, I'm drawing this kind of stretched out, but it comes back exactly to the same position, exactly the same height. You know what I'm getting at here? The displacement, the total displacement for the whole path is actually 0 meters. We're no longer looking at, okay, this is here, tell me what the whole height is. No, if we decide to look at the whole path, then the total displacement should be 0 because it comes back to the same point. So your total displacement, just like in the beginning of the year, you come back to the same point, your displacement 0. That still holds true, and it could be a useful piece of hidden information when doing the guess method. So don't forget about that. That's another thing to keep in the back of your mind. There's a lot of different, you have to be a savvy physics student and keep in mind all these different things and look at each scenario differently. A lot of times kids ask, like, is it always going to be like that? No, it's not always going to be like that. You have to look at the situation differently. Even this is only true if you're on Earth. And even when you're on Earth, it could be slightly different, very slightly different, depending on your location. But it's pretty much always negative 9.8. But if you go to the moon or any other planet, the acceleration might be different. So my point is, each scenario is different. You have to use your brain and think about it. These are just some tips and tricks that we can think about as we're doing them. So let's draw some graphs. So we'll look at the displacement versus time, we'll look at the velocity versus time, and we'll even look at the acceleration versus time. The displacement. In the displacement versus time graph, remember the slope represents the velocity. And think about the velocity here. The velocity starts positive, goes to 0, and then the velocity becomes negative. So that means our slope has to start positive, become 0 in the middle. The slope is 0, and then negative. And it does so kind of gradually. So it becomes just like that. And this is assuming the 0 position is here, and this is the positive. So the 0 position is at the origin, comes back to the origin, if you notice. Okay, so in the velocity time graph, the slope is equal to the acceleration. And the entire time, the acceleration is negative 9.8. And it's a constant negative 9.8. So I could actually jump ahead. The negative 9.8 should be down here. We know it's going to stay at negative 9.8 meters per second squared. And if we wanted to be specific, we could say this is 0 meters. And then what was our height? It was 11 meters, 11.025. So that's kind of cool. We could put some numbers on our graphs if we really wanted to. So the slope is the acceleration in this case. So what are we going to do about that? That means that if it's a negative slope, we want something that looks something like that. But does it go like this? Does it go like that? Let's look at the velocity now. So initially, the velocity is positive. So we're going to start with a positive velocity. Then the velocity becomes 0. So right at the maximum height, you're going to make this 0. And then the velocity is negative. So we could actually make this positive 14.7 meters per second. And then an equal amount on the negative side of things is negative 14.7 meters per second. And we're going to make a straight line coming down right here. This is my favorite graph right here because it shows the slope is a constant negative slope. And if you calculated that slope, it would be negative 9.8. So that's kind of cool. But when you look at okay, this is positive, then it's 0 in the middle, and then it's negative, that makes sense too. So it's kind of like a cool way to really know, oh, do I understand how to interpret graphs? And hopefully at this point, you do. So we could do this practice problem that says a softball is thrown straight up, reaching a maximum height of 15 meters. Neglecting air resistance, what is the ball's approximate vertical speed when it hits the ground? And what was the ball's hang time? So since they're telling you the maximum height, we're going to have to do like the partition method here. So it goes up, and then it comes back down. And this distance here is 15 meters. And we know nothing else. We know the acceleration is negative 9.8 meters per second squared. We know the maximum height is 15 meters. And they're looking for VF, the vertical speed when it hits the ground. Well, there must be something else that we could figure out. There must be another number. You need 3 numbers here. All right, yeah, so don't forget the velocity at the top is 0 meters per second. Now, do we want to look at the second half or the first half? Well, since they're asking for the final velocity over here, it'd probably be better to look at the second half of things instead of looking at the first half and finding out what this velocity is. You could do it that way, and then you just make it negative. But we'll make this the initial velocity. So VI is equal to 0 meters per second. We're looking for the final velocity. And right now, we don't care about the time. Time equals who cares. So the equation without time is VF squared equals VI squared plus 2AD. We're looking for VF. VI we said was 0, so that just goes away. 2 times negative 9.8 is negative 19.6 times 15. So you get VF squared is equal to the square root of 294. So then you take it's just equal to 294. Then you take the square root of both sides, and you get VF is equal to 17.5 0.15, so we'll call it 17.1, really 0.146, so we'll call it 17.1 meters per second. But is it positive or is it actually a negative velocity? If you look at our diagram here, the final velocity is going down, but my calculator spit out a positive number when I do the square root of 294. And actually, this is supposed to be negative 294, but you could just make it positive because who wants to deal with imaginary numbers? Not me. You just make it positive. But when you're calculating the square root of something, don't forget, all right, negative 17.1464 squared is still equal to 294. So don't forget that you could get a negative number too, and it still counts. All right, so that is now our final velocity. So we know that. What else are they looking for here? They're saying, what is the ball's hang time? What is T total? The total time that it's in the air. That's what they're looking for here. Now you could continue your analysis of just the second half. But if you found the time it takes to go from the top to the bottom, if they're asking for how long it was in the air, you'd have to take that time and then multiply it by 2. Which is a totally valid way to do it. You can definitely do it like that. I am going to look at the entire path. So we're going to see this is the total hang time here, okay? And the displacement is no longer 15. You could do it the other way if you like, hey, it says displacement is 15, and I like looking at the 15 thing because what you're about to write now is crazy to me right now. Well, you should get used to this, kiddo. It comes back to the same point where it started, so the displacement is 0. So we know this. We know the displacement 0. We just calculated this. I'm no longer saying VI is 0 meters per second because I'm not looking at that part of the path. I'm just looking for the total path here. So this is another valid way to do it. You could look at, again, you could look at the second half and then multiply by 2, but don't forget to multiply by 2. I see a lot of people do that and then they forget. But then I just ran into the trouble of, well, you don't know the initial velocity now, Mr. Dangle, so what are you going to do? Well, I do know the initial velocity. It's another savvy physics trick. So I'm just breaking out all the tricks for this one. Yeah, the displacement 0, and if we know it's symmetrical, then the initial velocity is equal to 17.1 meters per second. So there's a couple little tricky tricks that we can do here, but they're still valid tricks. It's symmetrical. So what is the total time? You have 4 pieces of information. You might as well do, I guess you could do VF equals VI plus AT. Whenever possible, I think that's kind of the easiest one to work with, so I try to do that one. 17.1 plus negative 9.8 times T. So then you solve. Remember, you're subtracting 17.1 from both sides. So this cancels out, but this doesn't. This becomes plus negative 17.1. This is negative 34.2 is equal to negative 9.8 times T. And now you should always get a positive number for T. And we do. We get 3.48979. I'm going to call it 3.5 seconds. All right. So, and if I divide that by 2, so for those of you who are like, screw all of this, I'm not going to do this crazy thing that you're saying, just make up stuff. All right, first of all, I'm not making it up. Second of all, you could do this if you want and just look at the second half. Make this VI. That's totally fine. You'll get a time of 1.74 seconds. How do I know that? I took this total time and I divided it by 2. This is for half. So since they're asking how long was it hanging in the air, if you did that, don't forget to multiply by 2 at the end and then do 3.5 when you round it seconds, okay? So yeah, there's a lot of different ways to do all these problems. As they say, there's more than one way to skin a cat, even this very sad looking cat over here. But that's about it. Thanks for watching and have a great day.